Look up at the night sky. For millennia, humanity has stared into the void and asked, where did we come from? What is the universe? The standard model says that 13.8 billion years ago, everything we know emerged from an extremely hot, dense early state, not an explosion into empty space. But what if we've been looking at the universe backward? What if the Big Bang wasn't the beginning of a universe, but the inside of a black hole? It's a question that sounds like science fiction, but it's one that a growing number of physicists are taking seriously. To find the answer, we must journey to the very edge of our understanding, where the laws of the cosmos bend and break. Let's separate myth from reality. Myth. If we were in a black hole, everything would be torn apart instantly. The very image of a black hole conjures destruction, an inescapable cosmic monster that shreds anything daring to approach. Reality. That's true for small stellar mass black holes. Their immense gravity is packed into a tiny space, creating an incredibly steep gravitational gradient. The difference in pull between your head and your feet would be so extreme. Their tidal forces would stretch you like spaghetti in a process gruesomely named spaghettification. Reality, but a supermassive black hole, one with the mass of millions or even billions of suns, is a different beast. Its event horizon is huge on human scales, ranging from millions to billions of kilometers across, light minutes to light days for the largest, not light years. Because its mass is spread over that larger radius, the gravitational gradient can be surprisingly gentle, so gentle in fact that you could drift across its event horizon and, from your local perspective, you wouldn't notice a thing. No alarms, no shaking, no spaghettification. You would have crossed the threshold into eternity without even knowing it. Myth. We'd see darkness all around. If nothing can escape a black hole, not even light, then surely being inside one would mean being plunged into absolute eternal blackness. Reality. This is another profound misconception. Inside the event horizon, light can still reach you from other things that fell in with you, or after you. Any light that crosses the horizon is trapped, yes, but it continues to travel inward, toward the singularity. You wouldn't see all black. Instead, you might see the light from stars and galaxies that crossed the horizon long ago, their images distorted and warped by the extreme gravity. The entire history of everything that has fallen in could be visible, all on its way to the same final destination. The event horizon is a one-way boundary for escaping, not for seeing. It's a barrier to information getting out, not a barrier to light getting in. So, if it's physically plausible to survive the entry and still see the light, this brings us back to the ultimate question: are we in one now? The short answer, based on all direct local observation, is that there's no evidence. We can measure our place in the cosmos with incredible precision. Earth orbits the Sun, which in turn orbits the center of our galaxy. We are located about 26,000 light-years from the Milky Way's central supermassive black hole, Sagittarius A star. This is far outside its event horizon. Our sun's gravity dictates the clockwork of our solar system. The planetary motions we observe are perfectly explained by our theories of gravity, and the way starlight travels across billions of light-years to reach our telescopes, all of it matches the physics of normal expanding space, not the extreme curvature you'd find near a local event horizon. But this is where the story takes a turn. What if the black hole isn't local? What if it's everything? Here's the cool and profoundly strange twist. It has to do with a staggering coincidence hidden in the math of Einstein's general relativity, first uncovered by Carl Schwarzschild in 1916. He calculated the radius to which any object must be compressed to become a black hole. It's Schwarzschild radius. The equation is simple. It depends only on mass. Some physicists, exploring the deepest implications of this math, propose that our entire observable universe could be the interior of a gigantic black hole that formed in a higher dimensional parent universe. If we estimate the mass of the observable universe and plug it into Schwarzschild's equation, the implied radius is of the same order as my 46.5 billion light-years, the scale of our observable universe. It's a striking coincidence, not proof. The math that describes the expansion of our universe, known as the Friedmann equations, shares structural similarities with equations describing the interiors of certain idealized black holes, though the spacetimes are not identical. This links the physics inside a black hole to the physics of expanding universes like ours. In this model, what we perceive as cosmic expansion is actually the inward fall of matter toward a central point, but stretched across a cosmological scale. This idea also addresses the issue of the singularity. Many quantum gravity approaches suggest matter cannot be crushed to an infinitely dense point. Some models predict a bounce, creating a new expanding region of spacetime. Such a big bounce could resemble a Big Bang to observers inside. It's an incredibly intriguing, though highly speculative framework. It elegantly connects the birth of our universe to the death of a star in another. But if this were true, what would be the evidence? What would give it away? The telltale signs of a black hole are its effects on time and light. Near a typical black hole, gravitational time dilation is extreme. Clocks run slower compared to those far away, and any signals trying to climb out of its gravity lose energy, causing their wavelengths to stretch. They get redshifted. Our best cosmological observations do indeed show a redshift. In fact, it's the primary evidence for the expansion of the universe. However, this redshift is isotropic. It looks the same in all directions. It maps perfectly to a model where space itself is expanding everywhere, carrying galaxies along with it, not to us being inside a single specific object with a center and an edge. Furthermore, we also see the cosmic microwave background radiation, the afterglow of the Big Bang, as astonishingly uniform from all directions, to 1 part in 100,000. This uniformity is a cornerstone of modern cosmology, and it's difficult to reconcile with the idea that we live inside a black hole, which should have a preferred direction, a center. We see the large-scale structure of galaxies growing over billions of years, forming a cosmic web of filaments and voids. All of these grand and beautiful patterns fit perfectly within the standard model of an expanding universe governed by general relativity, without the need for a surrounding horizon. So, to return to our myth versus reality, could a universe live inside a black hole? Maybe, in theory. The mathematics is tantalizing, offering a potential origin story for our cosmos. But does our universe, the one we can observe and measure, show the signs of being one? For now, the evidence says no. Our reality appears to be one of cosmic expansion, uniform and vast, a universe that, as far as we can tell, stands on its own.